So today we're going to start section 7.1 on slope fields and Euler's method. We will not get to Euler's method today, nor did I intend to. So in order to understand slope fields, first you have to understand something called differential equations. Any equation that has a derivative in it is a differential equation. Okay, we will do a very little bit of that. I don't want you to get the impression that you know everything there is to know about differential equations when we're finished with this, because at least it used to be in the engineering sequences in most colleges, you did 3 semesters of calculus and then a semester of differential equations. So there's a lot to learn, a lot to explore. We're going to scratch the surface of that. Okay, so the order of a differential equation is the highest order derivative. So if you have a third derivative involved, it's a third order differential equation. Okay, so for example, find all functions y that satisfy this differential equation. All we have to do is do the antiderivative. So the antiderivative of secant tangent is secant. So that's secant of x. The antiderivative of 1 over 1 plus x squared is? Yeah, tangent inverse or arctangent. Either way you want to say that. Plus the antiderivative of 2x. X squared. God bless you, I think. What was that?
Keep going.
Minus 3x plus c. That is sometimes called the general solution. Okay? Because there's lots of different curves depending on what c is. This one says find the particular solution to the initial value problem, dy dx equals e to the x minus 6e cubed, whose graph passes through the point 1, 0. Okay, so now we don't want just any solution. There's only one solution that's going to pass through this point and have this derivative. So again, we'll start by taking the antiderivatives. Y is equal to e to the x minus, let's see, that'll be 6 times 1/4 of x to the 4th plus a constant. So I'll simplify it a little bit before substituting. That's 3/2 x to the 4th plus c. Substituting in x is 0 and y is 1 gives us 1 minus, or should be equals, e to the 0, which is 1, minus 3/2 of 0 to, I'm doing it backwards, sorry. Take 2. So when x is 1, y is 0. So 0 is equal to e to the 1st minus 3/2 plus c. Solving that for c, we get 3/2 minus e is c. So our particular solution is y is equal to e to the x minus 3/2 x to the 4th plus e, plus 3/2 minus e. That is the particular solution. Now notice on this one that e to the x and negative 3/2 x to the 4th are defined for all real numbers. That's a continuous function. Okay, so we don't have to worry about any pieces. However, so that's the case where it says if the solution curve is continuous, then it pins down the solution to an initial value problem on the entire domain. However, if not, the initial condition only pins down the continuous piece of the curve that passes through the given point. Let me show you an example. You may be going, what the heck? Let's take a look at this one. So if dy dx is equal to 2x minus secant squared x. So taking the antiderivatives, y is going to be equal to what?
X squared minus tangent of x.
Right, plus a constant. That's not a continuous function because tangent is not continuous at all values of x. So what we're going to do is we're still going to find c, but then we're going to add on a restriction. We'll do that in just a second, but first let's solve for c. So 3 is equal to 0 squared minus the tangent of 0, which is 0 plus c. So c is equal to 3. So y is x squared minus the tangent of x plus 3. But we only are going to have one branch of this. Notice that the x value here was 0, right? What if we look at the graph of tangent and we include x as 0, we only have the principal branch, which goes between what two values?
Negative pi over 2 and pi over 2.
Yeah, negative pi over 2 to pi over 2. So that is our domain here. Negative pi over 2 is less than x is less than pi over 2. It only gives us that one branch. It doesn't give us multiple branches. So if the solution curve is discontinuous, you have to tell which branch it is that is the solution to your particular initial value problem. Yes?
What if the domain for the question is 1, 2, 3? Like,
I'm sorry, say again?
What if the question asks the graph passes through the point 1, 3? Is that instead of 0?
1 would still be in this interval because 1 is in between negative pi over 2 and pi over 2.
Like, what if they pass through this?
Oh, then you would have to give a different interval. So let's say, let's say that it went through 2, 3. 2 is more than pi over 2, so that would be the next branch over, which would go from pi over 2 to what, 3 pi over 2? So you'd have to give that branch. Yeah, that's exactly what happens. All right, page 2. So occasionally you get one like this. Find the solution to the differential equation f prime of x is equal to sine squared of x, for which f of 4 is equal to 9. We have a problem here. The problem being, I don't know what the antiderivative of sine squared x is. So what we will do is we will make use of the fundamental theorem of calculus. We'll say, okay, f of x then is going to be equal to the integral from some constant, I'll leave that blank for now, to x of sine squared of t dt. And you're like, oh, because if I take the derivative of this, whatever this constant is, I'm going to get sine squared x, right? So that part's good. You're like, well, I want, when x is 4, I want this to be 9. Okay, so what I'd like to be able to do is go, okay, I want this to be 0 when x is 4. Fine, I'll make the lower limit 4. And then I'll just go plus 9. Now, when x is 4, f of 4 is going to be 9. And the derivative of this is going to be sine squared x, because the derivative of the plus 9 is 0. Okay? That's the basics of differential equations in 5 minutes. Okay? Okay, next, slope fields. Slope fields are actually kind of fun. You may have heard that AB has started doing these already. We're in slightly different places because you guys have done like integration by parts and partial fractions and some of those other ugly things that they haven't done because they don't have to do them. That's one of the differences between AB and BC. All right, so a slope field is a graphical representation of the general solution of a differential equation. And I think the best way to understand how a slope field works is to actually make one. Okay? So construct a slope field for the differential equation dy dx equals cosine of x. Let's stop there and we'll do it right here on this little grid. Okay, so when x is 0, what is the cosine at 0?
1.
1. So I want these, when x is 0, the slope is going to be 0. So what I'm going to do is make a little mark across here with a slope of 1. Should be at a 45-degree angle. And that should be true everywhere where x is 0, right?
Yeah.
The y value doesn't matter. So these are all going to have a slope of 1. I'm trying to make them close to a 45-degree angle, but I get worse as it goes on.
Well, we need graph paper for the homework.
I made these for you.
No way.
Oh.
So no, you don't need graph paper.
He was so proud of that. He was very proud. Honestly, I'm proud of that too.
All right, so what happens at x is equal to pi?
It's negative 1.
It's negative 1, so all these are going to be negative 1. Directly in between those two is pi over 2. The slope is 0. So all these slopes are going to be 0. And then at 3 pi over 2, slopes are all 0 again. And when we get to 2 pi, they're all 1 again. You're just trying to make us look bad by doing them super fast. Hear this deek, 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 and I'm like, wow. And the same thing would repeat over here. And this is a very rough sketch. But you kind of get the idea. It's a little bit like if you guys ever looked at like a wind field or something like that, or a magnetic field.
Yeah.
Looks a little bit like that. All right. Now, find the general solution. Okay. The general solution would be y equals, the antiderivative of cosine is sine plus c. If I were to graph, say, sine of x plus 2, now let's do sine of x plus a half, because then it'll go through this point right here. It looks kind of like that.
Crazy. That's kind of cool.
It's almost like
It
looking at-
follows the slope field. So you can think of the slope field as being like little gates that tell it where to go when it gets close to that part.
Oh.
That wasn't very nice.
All right, so a slope field for dy dx equals x plus y is shown below. That's really hard to look at, and they're usually not quite that compact. And I know that's hard on the eyes.
Did somebody draw that, or is that like computer generated?
It's computer generated. Oh, gosh. All right, so a couple of things to analyze. When it says analyze the characteristics, notice that right in through here, we have a whole bunch of slopes that are really close to 0, right? And to the right of that, all the slopes are positive. And to the left of that, all the slopes are negative. So if they say analyze, do something like that. Talk about, I'm not going to take the time to do it because we're really short on time, but talk about where the slopes are 0, where the slopes are positive, where the slopes are negative. Do they get bigger as you move to the right, or do they get smaller as you move to the right? Those sorts of things are what you want to talk about. I'm not going to ask you to do that analysis on a test, nor will the AP, but thinking about it is a good thing. Okay? And it says graph the particular solution through the point 2, 0. So, and I know it's really hard to see this axis, but it's right here. 2, 0. So from that point, as I move to the right, I want to kind of follow these slopes. And they're getting steeper and steeper. Right? As I move to the right, these get steeper. As I move to the left, this kind of flattens out. And then starts getting steeper again. And right in here, I'm going like, I can't get across that line. So it looks something like that. All right. Page 3.
No, literally.
Does it bother your eyes?
You moved the paper like.
And you're like, I think I'm going to hurl. Yeah. All right. So here we're going to match each differential equation to the correct slope field. So a little bit of analysis really helps with this. For example, where is this slope going to be? Remember, this is a slope. Where is that slope going to be equal to 0? 0, 0 is 1 point. What are other points?
1, 1.
1, 1,
2,
2, 2.
Graph of X.
Any place where x and y are equal.
Whoa.
So I look at this and go, all right, where x and y are equal, that's right across this diagonal.
Well, yeah, I found it.
That's the only one that looks like that, isn't it?
Yep.
That's C. All right, for this next one, where are these slopes equal to 0?
0, 0.
When either zero. So
Exactly, where either one are 0. So either where the x's are 0 or where the y's are 0.
Huh.
Which is the only one of these that represents that?
D.
D. This one's a little more interesting. Where is this going to be equal to 0? When y is 0, what's going to happen when x is 0? It's undefined. So when y equals 0,
A.
well, let's see. When y is 0, that's along the x-axis. The slopes should be 0. And along the y-axis, they should be pretty much vertical. Yep. Now, here's the other thing we can look at on that. In the first quadrant, notice all the slopes are negative. In the first quadrant, x and y are both positive. Does that match this?
Yes.
Yes. All right, number 4, dy dx equals, yes?
Why is the graph of A got a half
Oh.
slope at origin?
This one, occasionally the program I use to generate these gets the yips near 0. And I didn't remember to take that one out.
Okay.
All right, how about this one? Where is the slope 0?
X is 1.
When x is 1. When x is 1, the slope is 0. Oh, that's E, right? And I want you to notice something. As I move up and down, do the slopes change?
No.
Because there is no y in the differential equation. Likewise, this one, yeah, there's no x, so as I move left and right, there should be no change. What am I left with? B? And notice as I move left and right, no change in the slopes. Okay. And wow, am I really supposed to do Euler's method today too? Yikes. Tell you what, because I mean, there's no way we're getting through Euler's method. If you have any ones on homework that say use Euler's method, wait on them.
Okay.
Okay.
What if I have this condition where every problem says use Euler's method?
You have that condition.
Yeah.
I actually
It
can't
just
do
happens.
any of the problems
Just looks
without
as well as
doing
cousin.
Euler's method.
I just read it and it says